All right, so hello everyone. Thanks Mike and thanks Subit and Jennifer for organizing this great initiative. It's my pleasure presenting today. My name is Amro Awad from the ECE department, and today I will be talking about what we do in my research group and our future plans. So a little bit about myself. I have my PhD back in 2016 from NC State. Later, I joined Sandia National Labs in Albuquerque, New Mexico. I joined UCF since fall 2017 with several research stints in a couple of industrial research labs and government labs. I was also Air Force faculty fellow, and I every now and then do some community service and community services for my academic community. So what's new in computer architecture? We have emerging memory technologies. Notably, there's emerging non-volatile memory technologies that hold characteristics of both storage systems and main memory. Any of you who know, storage systems are typically can be represented by hard disk drives or flash devices that are typically very slow, but they are non-volatile, which means that your data remains there and you can keep your files persistently there. Meanwhile, you have DRAM, which is pretty fast, reasonably fast, but it's volatile, which means that as soon as you have a power outage, you have lost your changes to your Word documents or anything that is stored in the DRAM. So what is unique about these emerging non-volatile memory devices that they hold the characteristics of both, or the best of both worlds. They are both fast and non-volatile, which is uniquely merging the storage and memory systems into one thing, and that's pretty exciting. We also have new compute paradigms. We have cloud computing, edge computing, near memory computing, domain-specific architectures like AI accelerators and whatnot. So all of these are new in computer architecture. As we are doing this, there are new challenges, and such new technologies and emerging paradigms require rethinking software architecture, system assumptions. It also requires rethinking our hardware architecture and support to better embrace for the arrival of these technologies. And finally, there are security concerns of such new architectures or new technologies that need to be basically considered ahead of time before even we integrate such technologies or new paradigms or architectures in our systems. So a little bit about some of what we do in my research group. So we have funding from different agencies, and we look at a couple of different things, including performance, power, and security of next generation computing systems. So we are funded by Navy to look at secure and deterministic safety critical systems, where we are trying to improve the performance predictability of safety critical systems. You can imagine weapon systems or autonomous cars, anywhere where predictability is important. We also look at security of NVM hosted file systems and secure NVMs when they are used as main memory as well. We also look at secure fast storage and how to implement this efficiently. We also look, along with Sandia National Labs, at how do we design memory-driven architectures and architectures that are basically centered around large or massive capacities of memory pools. We call this, for now, disaggregated non-volatile memory systems. Additionally, we look at secure accelerators and in-memory computing, where we try to identify new security primitives and constructs that are suitable for accelerators and in-memory computing paradigms. We also look at security of emerging technologies like virtual reality and 3D printing. So for the rest of the talk, I will be mainly talking about one example of a new technology and the problems we are trying to solve on it. It's really part of our efforts in on my group. So Let's first talk about emerging non-volatile memories a little bit more. So their performance is typically comparable to DRAM. However, they offer huge capacities. We are speaking of terabytes per processor socket, which is, we can safely say, perhaps hundreds to 1,000 times larger capacities than we have now in our current systems. Given that it's non-volatile or persistent, it allows crash-consistent systems or recoverable systems. If we have power outage, still our data will be there in the memory, and we can, rather than losing everything or restarting from scratch, we could have actually crash-consistent systems or recoverable systems. It's also ultra low idle power. It's unlike DRAM, does not require frequent refresh operations. And in terms of challenges, from security standpoint, emerging NVMs have data remnants vulnerability. So your data stays there, and this means larger attack surface. You can easily apply physical attacks and try to obtain information from them. They have limited write endurance, so you can write these NVM cells for a few million times before they wear out. And finally, they are slow and they have slow and power-consuming write operations. So we need to keep this in mind when we are doing anything around NVMs. So now let's talk about what secure memory systems are. As you can see in the figure, there is a processor chip connected to memory modules. Typically in secure memory systems, your trust base is the processor chip. So when the data leaves the processor chip, its integrity and confidentiality has to be protected. For instance, when you are sending out your data outside the processor chip, it has to be encrypted and decrypted only when it arrives back to the processor chip. Same as for integrity, we need to ensure that whatever we have written to the memory is actually intact. No one has tampered with it. There's commercial support for such security primitives or features like AMD's secure memory encryption, Intel's safeguard extension, Intel's total memory encryption. However, when we try to implement such secure memory system with NVMs, there's like lots of problems we find. In particular, encryption exacerbates the write endurance issue, and we looked at this problem in the past, and the community looked at that as well, where encryption itself exacerbates the write endurance. Due to the diffusion property, a single update in 1 bit can lead to lots of updates. It also has high performance overheads due to slow write operations for some security supports, namely oblivious RAM and integrity tree updates. We have also security metadata. Security metadata has to be crash consistent and synergized with data, which means that even though data is NVM, we need to make sure the security metadata is accompanying the data itself across systemic crashes. So some of this work has been done in my group, some was done back during my PhD. So our recent work, this is funded by DARPA. What we do is we look at efficient, secure NVM implementations that ensure recoverability, high availability, and resilience of the system. We have some of these works published in top conferences, namely Osiris, Anubis, and recently we have work related to resilience, and that's called Soteria. We also look at how we can implement such secure NVM implementations on FPGA and hardware prototype it to better assess its power, performance, and area overheads while we are trying to figure out what is the best design and implementation. So that's pretty much it for collaboration possibilities. I'm mostly interested on compiler support for emerging memory architectures and of course security. I think there is lots of new security technologies such as, you know, memory protection keys by Intel and even trusted execution environments that lack efficient compiler support. So I'm interested in looking at that, and this is something I would love to collaborate on. Also, hardware support to protect AI models and proprietary systems, designing domain-specific architectures for emerging applications, security of and privacy of healthcare implants and intermittent power devices, security support and privacy preserving techniques for sensitive systems. This includes smart grids and other physical systems, and finally, security of in-memory computing. So that's pretty much all of these are possibilities, and I currently have active collaborations with several faculty members at UCF, and those led to many exciting projects and publications, and I'm certainly open for new collaborations. Thanks everyone for listening and questions.